Okay. Now, finally answer your question. We found at the end that our set of constraints, we didn't get 4 independent constraints. What we found is, at the end of this, is that one of them was dependent on the other ones. It didn't add any additional information. This was actually, we've seen this before. If we were looking in 2D, we saw a line like this and a line like this. That was two independent constraints. I'm using the term independent loosely, but it is a technical term, and we'll come back to that soon. We have two independent constraints, and that determined 1 point, right? We could have possibly added another constraint to this without making our system over-constrained, which was another line that goes straight through that point. That's exactly what we ended up with in this situation. Was one of these constraints was just kind of worthless. Okay, any other questions? I'm really going to convince you all to ask more questions. If I just create an awkward silence for a minute. Also give me a minute to catch my breath. Okay. I guess that's how I know that this is a good mask plate. I take a breath and it just kind of suctions to my face. Okay. Now, actually, I do want to go from the book for this one, because I want to make sure that I phrase it in the same way. This matrix, the one that we've ended up with, is in a special form, and we call this the first word is optional, row, echelon, form. Intuitively, what this means is that if we look at, in each row, how do I want to introduce some terminology? Yeah, so this is terminology from the book. Leading term. So the leading term is the first non-zero entry in each row. Okay, so this is the leading term in row 1, this is the leading term in row 2, this is the leading term in row 3. Row 4 is just a 0 row, and so we don't care about that. Okay, intuitively what this means is that as you go down from top to bottom, down the rows, the leading term is kind of marching to the right. This echelon is sort of like has some military origin. Anyway, we have these kind of moving forward as we go down, the leading terms. So that's what row echelon form is. And it has some special properties, and I want to make sure I mention all of them. Number 1, well, I will reword them a little bit. All the 0 rows are at the bottom. Is my phone still running? Is the battery died?
No, it's still going.
Okay, perfect. Don't read any notifications I get. Okay. All the 0 rows are on the bottom. And we've got that. At the bottom here, this was a consequence of, as we were looking for the pivot, whenever we found one that had a 0, we shifted that to the bottom. So all the 0 rows get shifted to the bottom. Okay, property number 2, I think, is what I just said, which is each leading entry of the row is, yeah. So you can and should and must read the book, and it says this in a different way, but I'll say it like this. As we move from top to bottom in the rows, the leading first non-zero term in the row. Move from left to right. Okay, and we've got that. Here, here. Here it didn't move just one, it moved two, and here it is gone. Right. Okay, and the third one, the book says all entries in a column below a leading entry are zeros. That's fine, it is. So everything below a leading term is zero. And again, we have that. Zeros, zeros. Everything below a leading term is zero. In this case, there's no leading term, so everything below it is nothing. All of those nothing are zero. What we call vacuously true. Okay, so this is, what did they call this? This is the row reduction algorithm. I'll use the same terminology. Yes. So the algorithm which is described is called the row reduction algorithm. And it follows these three sort of simply stated instructions. No, these are the instructions. So it's four of them. 1, 2, 3. The book makes these one thing. If I write go to step 1, anybody in here that does computer programming? Yeah. So you recognize the go to, something you're never supposed to be using. Well, we're going to use it right here. Okay. So this is the algorithm. Well, these are steps that are stated at least specifically enough that we could convince a computer. We could program a computer to do it, which I guess is kind of like convincing it. But yeah, this is similar to, for example, the multiplication algorithm, where we have just a series of steps that we follow, and we always get an answer. Now, this algorithm always results in a matrix that is in echelon form. So what do we want to do next? There's something that's supposed to be special about this. The book will actually use the fact that we can turn a matrix into an echelon form matrix, an echelon matrix. That's row equivalent. Remember, we said this is row equivalent. To prove a lot of different things. So it'll prove a lot of different properties about matrices based on the fact that we can do this. So that's very useful. Also, I want to point out that we did have a bit of a shift in our point of view when we did this. We started with a system of linear equations, and what we're concerned about is common solutions to all of these equations. And we transferred this into a matrix, which is just a grid of numbers. And now there's nothing in these steps, there's nothing in these properties, nothing says anything about solutions, right? We're purely looking at this as just a blob of numbers, and that's it. Okay, so maybe now what we want to do is go back in the other direction and say, oh, it's nice that we've almost turned this into a game, right? It's like a puzzle, and we're just solving a puzzle. This complicated thing that looked like lines intersecting in 2 dimensions and planes intersecting in 3 dimensions, things that are impossible to imagine in 4 dimensions or 5 dimensions or 100 dimensions, or 1,000,000 dimensions or infinite number of dimensions. And we've turned it into basically a game, and also something that we can tell a computer how to do. like Sudoku. Okay. So let's go back in the other direction and let's try to figure out what this says about solution. Well, what did we end up with? We ended up with a system of equations from this. The first thing, do I want to, can I erase this? Has everybody written this? Okay. Everybody that wants to, oh, it's being recorded here. That too. I'm not used to this. Using technology in class. I like to do everything on chalkboard. Okay. So we got plenty of room, and we can say, what is this system of equations? Oh, this is a nice practice. X1 plus 4, x2 plus 5, x3 minus 9, x4 minus 7, x5. Okay. Nope. Nope. Equals 7. I'm treating this as an augmented matrix, not as an ordinary matrix. Minus 7. Minus. Yeah. Okay. Now, this one. So we've got 2 x2 plus 4 x3 minus 6 x4 equals -6. Now that's significantly easier than the one before it. It gets even easier. Minus 5 x4 is equal to 0. And finally, what's our last constraint? 0 equals 0. Absolutely true. This one, I know that's definitely true. Okay. 0 is equal to 0. So we're coming to your question from before. What is this saying about the system of equations? It's saying 0 is equal to 0. Okay. So we've discovered something very deep in mathematics. 0 is equal to 0. But we also have other stuff that we can do with this. We can now get the value of x4. Actually, x4 is equal to 0. And then we can plug that back in here, and we get that these two, well, we'll get x2 in terms of x3. Okay. And plugging x4 back in here, we get x2 in terms of x3 here, and so we ultimately get x1 in terms of x2 and x3. Now this is what we were talking about the other time about figuring out what the variables are in terms of the other ones and plugging them in. And what we agreed was that this is the same as taking one of these equations, multiplying it by some multiple and adding it to the other ones. So let's look at it from that point of view. That will bring us to the next part of our, so they put this all in the same algorithm. That's okay. So we had a step 4. No, step 4 was separate in the book. Okay, step 5. So we're going to get an extra step to this. Step 5. Divide each let's state this differently. Use each pivot to I want to state this. I got it now. Scale each row so that the pivot is equal to 1, and then use the pivot to eliminate all entries above it. I'm back in the world of thinking about this as just a grid of numbers. Okay. So I'm gonna turn each pivot into 1, and then I'm gonna eliminate everything above it. This is what they did call this scaling, right? Let's just say they did. So this row operation is called scaling. And we'll go over to the right here and continue on. So the scaling I'm gonna do is I'm going to divide this by -5. Well, that's gonna be easy. 1, 0, 0, 0. 4, 2, 0, 0, 5, 4, 0, 0, 9, 6, -1, 0, -7, -6, 0. That's, my writing is getting worse as we go on. Okay, now I'm going to use this row to eliminate everything above it. That's going to be pretty easy, right? Because all the other entries are 0. So when I multiply this by something necessary to eliminate these two things, all this other stuff isn't going to change. So I'm going to cheat a little bit. I'm going to do the row operation. I'm just going to do it on the same one. I'm going to say these are 0 now. So eliminate that. Next, are we almost out of time? We're out. The rest of this example is in the book. So there you go. I'm not gonna be in my office today. If anybody was wanting to go, I won't be there. I have an appointment I have to go to. We'll probably stop recording now. That doesn't need to be part of the class record.